Today we're going to be discussing similar figures. And shapes are similar if they have the same shape, but not necessarily the same size. And if you'll see, these two quadrilaterals are similar to each other. One's just obviously bigger. And so this right here is our similarity symbol. Now, when you have similar figures, or when you want to create similar figures, you use what's called a scale factor. And a scale factor is the ratio needed to multiply a figure by to make it proportionally smaller or larger. So it's basically a fraction that you multiply an original figure by to get a new figure that's smaller or larger. To go from a small shape to a larger shape, your scale factor is going to be greater than 1. And if you're going from a large shape to a smaller shape, your scale factor is going to be between 0 and 1. To find the scale factor of similar figures, you take one of the lengths of the new shape and divide it by the corresponding length of the old shape. So that's the ratio you use to find a scale factor. It's new over old. For example, let's say this small triangle is our old shape, or our original one, what we started with, and we made it bigger. And so this one's considered our new shape. So old's what you started with, new is what you ended up with. And let's say they're equilateral triangles. The old one had a side length of 4, and the new one had a side length of 28. Well, to find the scale factor, you take the side length of the new, 28, and divide it by the corresponding side length, 4, of the old shape, and simplify that fraction, and you'll get 7 over 1. So that's your scale factor from old to new. So that means that our new figure is 7 times bigger than our old one, since we just multiplied the old one by 7. Now let's say we're going to go from a bigger shape and make it smaller. So we have these two pentagons. We'll call this bigger one our old pentagon. That's what we started out with. And this new one we've made smaller. So we started out with a side length of 42 units and now have a side length of 6 units. So again, to find that scale factor, you take the side length of the new shape, which is 6, and divide it by the side length of the old shape, what we started with, which was 42. And again, you simplify that fraction, and you get the ratio of 1 over 7. So that means our new shape is 1/7 of the size of the old shape. And how we got that is we take our old measurement, 42, and multiply it by our scale factor of 1/7. Now we're going to go over applying this to the side length, surface area, and volume of shapes. So we're just going to go ahead and call this smaller prism our old shape, and the larger one our new. So we started out with the smaller one, we made it get bigger, so we know that the scale factor we're going to find for the side lengths is going to be, let's say the side length of our old one is 5 by 3 by 3, and of our new one is 15 by 9 by 9. To find the scale factor of the side lengths, it's what we just went over. You do new shape over old shape. So we have the side length 15 for our new over 5 for our old, since those are the two that correspond to each other. Those are the front lengths. And then you simplify that and you get 3. So our scale factor for the side lengths is 3. And you can do that for any of the side lengths. We could have done that with 9 and 3, and guess what? You'd still get the same scale factor. And so what this means is that the new shape is 3 times larger than the old shape. So let's write that down. The new shape is 3 times larger than the old shape. And now we can go over the scale factor for surface area and volume, and those are actually going to be a little different. When we did it for the scale factor of side length, we're just talking one dimension. We're just talking the length, or we're just talking the width, or we're just talking the height. When we go to surface area, we're now talking 2 dimensions. So let's see how that changes. Now, we haven't covered surface area yet, but to find the surface area of a prism, you basically have to find the area of each face and base of the prism. Now, since we're going to get into that later, I'm just going to go ahead and tell you the surface area for each of the prisms, so that way we can get to what the scale factor looks like. So the surface area for the old shape is 78 units squared, and the surface area of the new shape is 702 units squared. And again, just like our scale factor says up here, we do new shape over old shape. We're going to take that new surface area and divide it by this old surface area. So that's going to be 702 divided by 78, which simplifies to 9. So for the side length, our scale factor was 3, but for surface area, it's 9. So how do we go from 3 to 9? Well, 3 is just like saying 3 to the first power, and 9 is like saying 3 to the second power. Since we're in the second dimension, we have length and width now. You square your scale factor of 3 to get 9. So when you're doing surface area and you're coming up with its scale factor, you take your scale factor for the length and you square it. So guess what's going to happen when we go on to volume? I'm assuming you're going to think that we're just going to cube the scale factor of the side length, because we're now in 3 dimensions, length times width and times height. And that indeed is true, but just to check, we'll go ahead and go over it. So again, we haven't gone over volume of prisms, so I'm just going to go ahead and tell you what they are. And if you do want to know, you literally just multiply your 3 dimensions, since this is a rectangular prism. So the volume of the old would be 5 times 3 times 3, which is 45 units cubed. And the volume for the new would be 15 times 9 times 9, which is 1,215 units cubed. Again, to find the scale factor, you do new over old. So 1,215 divided by 45, which simplifies to 27. And guess what? 27 is 3 to the third power. So you take your side length scale factor and you raise it to whatever power associated with that dimension. So for side length, we are only dealing with 1 dimension, so that's the first power. With surface area, we're dealing with 2 dimensions, so that's the second power. And with volume, we're dealing with 3 dimensions, so that's the third power. Now we're going to go over how to determine if figures are similar. So to do that, you have to compare the ratios of the corresponding sides. And if all of the ratios reduce to the same fraction, then the figures are similar. So let's go ahead and check quadrilaterals ABCD and EFGH and see if they're similar. So we're going to take the ratios of all sets of corresponding sides. First one we can look at is A to B. That goes from the 3 lines to 2 lines, and that's 5. So I'm going to check that with the 3 lines to 2 lines here, which that's 2.5. So I'm going to do 5 divided by 2.5. And that simplifies to 2. Then we can check another side length. So 2 tick marks to 1 is 6 on the first, and 2 tick marks to 1 is 3 on the second. Those again simplify to 2. So we'll keep going. 4 tick marks to 1 is 7. 4 tick marks to 1 is 3.5. That again simplifies to 2. And lastly, 4 tick marks to 3 is 4, and 4 tick marks to 3 is 2, and those again simplify down to 2. So all 4 of the corresponding sides have a ratio of 2, which means they're similar. Now, you could have done it the other way and done smaller shape over larger shape, and you would have gotten 1/2 for all of those. That's fine. It doesn't matter which way you do it if you're just trying to tell if they're similar. You just have to make sure you do it the same for each set of sides. So with this scale factor of 2, that means to go from small shape to large, we'd multiply by 2, and to go from large shape to small, we would divide by 2. And since these figures are similar, that means that all of the corresponding angles are congruent. So they're exactly the same. But the sides, they're not congruent. They're just what we call proportional because they all have the same ratio. For this example, they all have the same ratio of 2 to 1. So we can say all corresponding sides are proportional because they all have that same scale factor. And since all of that is true, we can write a similarity statement. If you remember back from a couple chapters ago, a similarity statement is just stating what two things are similar. So we did this with a congruence statement. We stated which triangles were congruent. Now we're stating which ones are similar, so it works the same way. Each point that you put in your similarity statement has to correspond. So if I'm going to call my first quadrilateral ABCD, then I have to say that's similar to quadrilateral EFGH because A corresponds with E, B corresponds with F, C corresponds with G, and D corresponds with H. And we know that because of the markings on the figure. And so that's how we write a similarity statement. Exact same as congruent statement, except instead of the congruent symbol, we use the similarity symbol. That's it for these notes. So you can go ahead and fold them and tape them into your notebooks. And you can title it, I spelled title wrong. You can title it Similar Figures. (7.2)